Previously, in the earlier module, we have been shown the property diagrams PV and TV, and the isobaric lines in black, isothermal lines in red, and isochoric lines in green have been shown on the property diagrams. You can also indicate the state of the working fluid of your system on the property diagrams. Let's say if you know the pressure of your system and the temperature, so the intersection of those two lines will show the state of your working fluid. And here you can also get your volume shown here on the TV diagram. And in the last module, it is stated that with the state postulate or the two property rule, knowing two independent properties, you can describe the state of your system. Yes, so pressure and temperature are two independent properties here, and you may get your volume here, a specific volume that is. So what about other properties? Well, you can get them from the property tables. Knowing P and T or P and another property, we'll see much of these property diagrams and the properties themselves in the second module. That is the state of pure substance. Okay. So we move on to pressure. Yes. Pressure is just force exerted by a solid is called stress. By a fluid per unit area is pressure. The units used are Newton per meter squared or Pascal. 1 Pascal is 1 Newton per meter squared. Or bar is 10 to the power of 5 Pascal, or 1 atmosphere, which is equivalent to 1.01325 bar. Okay. So pressure at the point in the fluid at equilibrium is the same in all directions. Now in thermodynamic analysis, we are concerned with absolute pressure. Yeah? For any analysis performed on a thermodynamic system, you need the absolute pressure, but it is measured relative to absolute vacuum. Most pressure measuring devices, however, are calibrated to reach zero pressure in the atmosphere. So you see, if you have a pressure gauge connected to a system and it's telling you that it's 5 kilopascal, in order to get the absolute pressure of the system needed for thermodynamics analysis, you would have to add that gauge pressure to the atmospheric pressure to get the absolute pressure. That is using a pressure gauge. For vacuum gauge pressure, that is if your pressure is let's say minus 5 kilopascal, the vacuum pressure would indicate it is just 5. It's a vacuum pressure. So this is better described with the schematic diagram here. So if you have your vacuum pressure, you want your absolute pressure, you would have to get the atmospheric pressure, subtract the vacuum pressure to get the absolute pressure. For the pressure gauge, that showed a reading. To get the absolute pressure, you have to add that to the atmospheric pressure. Yeah? Be clear about that. Okay. Let's say the pressure gauge is not being used here. So, but you can measure the difference. Yeah? If the system, in this case gas, the tank of gas, is connected to a manometer U tube, in the shape of a U. Yes. So you want to know the pressure, the absolute pressure of the gas in the tank without the pressure gauge. So here, you see pressure at location 1 and pressure at location 2 are the same. So you want to know the pressure at location 1 exerted by the gas. So knowing the pressure at location 2, that will be equal to the pressure at location 1. But what is the pressure at location 2? If you do a schematic of the free body diagram, you know that the pressure at location 2 is just the atmospheric pressure exerted there and the weight of the height of the manometer fluid H. Yes. So you do conservation of forces, force balance. Yeah, you will get that the pressure at location 1, which is equal to pressure at location 2, being equal to the P atmospheric plus rho Hg. rho here would be the density of the manometer fluid. G is the gravitational force, about 9.81 meter per second squared. You can have a look at the example 19 in the eBook. Yeah. Atmospheric pressure. Yes, we need atmospheric pressure in order to get absolute pressure if we are given the gauge pressure. Yes. So atmospheric pressure, or we call barometric pressure, is normally measured with a barometer. Yeah. So a force balance on the free body diagram again will tell you that the pressure at location B is just the rho Hg, the pressure of the atmospheric. Yeah? The same as at that location B. The vapor pressure here at A is negligible, so it can be ignored. So you can get atmospheric pressure from the height of the barometer liquid. And normally it's used mercury, but other liquids can be used too, like alcohol. Now, a frequently used unit is a standard atmosphere, defined as the pressure produced by a column of mercury, 760 mm, in height at 0 degrees C. Yeah. Pressure is also sometimes expressed as the height of the mercury itself. You don't give it in kilopascal or bar, but in 760 mm Hg. Please proceed to example 1618 to see how the calculations are involved. Now, there are two questions here to ponder. The average atmospheric pressure decreases with height above the sea level. Can you see why? Also, the average atmospheric pressure changes depending on the weather conditions. We can discuss that the next time we meet. Next, we go to the temperature and zeroth law. Temperature is one of the thermodynamic properties which is difficult to define. Why is that? If you are in a room at 20 degrees C and you touch a metal chair or in a wooden chair, they happen to be in the same room, you would have felt that the metal chair somehow felt cooler. But we cannot depend on our sense of touch. The zeroth law states that if two bodies, say A and B, are in thermal equilibrium with the third body C, they are also in thermal equilibrium with each other. Yes, we have come across this in the first module. Yes. Thus, we define the equality of temperature, that is, two bodies have equality of temperature, the third body being the temperature measuring device, the C. Yeah, when they are in thermal communication, no change in any observable property occurs. So it's actually the temperature measuring devices are based on the zeroth law. So how do we use temperature measuring device? It's based on the thermometric property. Thermometric property is a property of a material that varies with temperature, e.g. volume of a liquid. If you have mercury in your thermometer, as the temperature, as the surrounding gets warmer or hotter, the volume of mercury expands. Yeah? So the volume is the thermometric property. Yeah? For helium, the pressure expands. Yeah? So these are the properties in materials are needed in temperature measuring devices. Temperature scales. Yes, we have known earlier that we are using the SI units, so it's degrees Celsius. Formerly it was centigrade, but don't be surprised, some pilots still use the degrees centigrade as recent as last year when I was flying somewhere. Okay, so here we look at Kelvin. Yeah, remember that temperatures in engineering are measured in Kelvin. Yes, this is for the United States unit, but in this course we are looking at Kelvin and degrees Celsius. That is the last part of the module 1.